Okay, this is our foundation paper for Physics Paper 2. We can see a skydiver in the image in Figure 1, and it says the skydiver is accelerating downwards. Now that is a really important word. So when we get to 1.1 where it says which force causes the skydiver to accelerate, we need to think about what is making them speed up as they go towards the ground. And we have this force that is always pulling us downwards, and that is our gravitational force. And it's thinking about that. Which direction is the skydiver going? They're going down, therefore gravity is going to make them accelerate towards the ground. Which force increases as the skydiver accelerates? Again, we're thinking they're moving down, that's our gravitational force. And which of this force is going to increase? Well, if we have our skydiver here and we have gravity acting downwards, you should know from a skydiver as they speed up, as their velocity increases, the opposing force also increases, and that is air resistance. So it's very much just testing whether you understand that as you increase your velocity, the air resistance or drag will also increase. Figure 2 shows the two forces, a little bit like the diagram I just drew. Now again, this is testing, calculate the resultant force. So that's the important bit, the resultant force, where we are going to do 600 take away 150, because the force downwards take away or subtract the force upwards, acting upwards, is going to equal 450 newtons. Eventually, the skydiver stops accelerating and falls at constant velocity. Again, all these terms are really, really important to understand. Well, what is the resultant force acting on the skydiver when falling at constant velocity? Well, if they're accelerating, as we saw in the previous question, there is a resultant force. It was 150. For constant velocity, for this skydiver, it means the force acting upwards is going to be, let's say, 400. The force acting upwards is going to be exactly the same as the force acting downwards, so our resultant force is going to be 0 newtons. What name is given to the constant velocity of the skydiver? Again, specific to this question, specific to this model and example, if they are going at constant velocity, this constant velocity bit, it's not average, it's not initial because it's not at the start, it's terminal velocity. This is the fastest, the maximum velocity they can go with those forces involved. Figure 3 shows a velocity time graph. Okay, so this is how we do it, where how many seconds did the skydiver accelerate for? Well, you need to understand what a velocity time graph is. This is our motion. We have velocity and time. If we do change in velocity divided by time, we are accelerating. So therefore, we need to work out when they stopped, when he stops accelerating, or when his velocity remains constant. Well, we know, beautiful drawn straight line there, his velocity ends up being 46 meters per second, but at what point does it start being 46 meters per second? Because that is the point at which he stops accelerating, and we could say 20, I think it's just before 20. It's probably more like there, which is potentially 18, 19. I'm going to say 19 seconds, but in reality, for the question like this, there is a little bit of a range. It can be anywhere between 18 and 21 seconds, because there is a bit of a range as to how you read that graph. Same graph, exact same graph. What was the constant velocity? Well, this is where if you look at a graph and try and look for all these different points first, it makes it far easier. We've already done this. Draw with a beautifully straight line. It comes across to 46 meters per second. And again, that's your velocity you're going across the y-axis. After opening a parachute, the skydiver fell at a constant speed of 3.6. Now, calculate is important. It means we're going to use a calculator, and they've given us our equation. So how we write it is important. If you want to write distance traveled, that's not a problem at all. Okay, they've given you that, and that's acceptable. Some people might want to write s as distance. On your equation sheet, it will say, give you both of these examples or options. They give you the speed in the question because it says speed is 3.6, so we've got 3.6 in each of our examples, and then we always do the function, which is multiply, and time is our 25 seconds. It's our 25 seconds. If we do those together, that equals 90 meters. Now, the 2 marks bit, that tells you something. You get 1 mark for substituting in the values and 1 mark for using your calculator and writing it down. Any more marks than that, you're doing more math than we've just done there. Okay, how does the force on the suitcase compare with the force on the Newton meter? Well, we need to look for what is happening, the motion of this, and this is important within this. If there is motion, if there is movement, then it means the forces are not going to be unbalanced, but it doesn't tell us there's movement. It just tells us, where does it tell us that there is a pair of forces acting between the suitcase and the Newton meter. It doesn't tell us movement, which means the forces must be the same size. Otherwise, there would be movement. Which sentence describe the directions in which the pair of forces act? Well, they're always going to act in opposite directions. Every time we've drawn, or we ever draw forces, there's always going to be a pair of forces acting in opposite directions. Usually with a figure like this, if there are numbers involved, they'll get you to measure or read off of the numbers as much as possible, like the graph in question 1. What is the weight of the suitcase shown in the Newton meter? Well, we're looking here, and again, they need you to recognize that you're measuring it that way round, and if you measure it correctly, it is 196 newtons. Now, how did I know it was 196? Because I count how many tiny little squares there are in between the 0 and the 20. That's easier to do, and there are 10, which means each one of those little gaps is worth 2. And if we go over to the black one, that is 2 gaps before 200, so it must be 196. Okay, I've shown this again. What is the weight? It's the exact same question on the previous one where we've got 196, but it's one of those where if you've got the wrong answer, you can still get marks for the next question. So if you've got 200 or 180, if you use that number, you will still get marks for it. Okay. Use your answer. It says it in the question, so don't worry about, oh, I think it might be wrong, I guessed. Just use that number again. Now we have mass, again, equals, and we have decided our weight is 196, and then we're going to divide that by 9.8, which is what they give us in the question, gravitational field strength, so that bit there. And if we do that in our calculator, it's going to be 20 kilograms. Again, we've only had to substitute numbers in, so it's not going to be a large amount of maths we have to do. Okay, this is a really good question, although it seems quite complicated actually, because you've got this graph, lots of information above it. If we go right down to the question, it says, describe how the weight of the suitcase will change during the first 25 minutes of the flight. Okay, you can look on the graph, it has time up to 30 minutes actually, and the gravitational field strength. But crucially, it says use figure 5. I think that is a really important bit because it gives you a clue as to what you need to start talking about. And also, always look at the marks. It's really important to look at the marks. 3 marks means you're going to say 3 things. And if you look at the graph, there are 3 parts to this graph. There's part number 1, there's part number 2 where it actually changes, and then part number 3 at the end after it's changed. So all we need to do is describe those 3 parts of our graph, and we're good to go. So what can we say? Well, for the first bit is I would always say, as the time increases, always start with the x-axis, as the time increases, the gravitational field strength, long word gravitational field strength, I'm going to shorten it, decreases. Okay, that's our first mark, straight away. Now, what happens at 2? That's the moment at which it changes. If we go down, we can say until 15 minutes. That's when that change happens. And then after 15 minutes, what happens? After which, or after 15 minutes, the gravitational field strength remains constant. It's really important you look at the number of marks for a question like this, because the number of marks will make a difference. If it was a 2 mark, you might not have to say a certain aspect of it, but this sort of thing where there are 3 distinct parts, you're going to say 3 marks worth of things. Okay? Okay, we have a referee in a football match. When the button is pressed, the whistle emits sound waves that travel through the air. What is transferred by sound waves? Actually, what is transferred by waves, generally? This is one of those key parts of information, key points of information you need to know about waves. Waves transfer energy. Always, whether it's a light wave, whether it's a sound wave, whether it's electromagnetic, or ultraviolet, or gamma, they all transfer energy. What is the typical value for the speed of sound in air? Again, one of these random little pieces of knowledge you need to know. 33,000 meters per second is insanely quickly. Just like 33 meters per second isn't that quick. It's somewhere in the middle, which is 330 meters per second. Okay, we've got 2 waves, wave A, wave B. Complete the sentences. So I always think it's important to read carefully because it says choose the answers from the box. It doesn't say you can use the answer more than once, and that's important because that's almost a hint that you should. And this doesn't say it, which means we're going to be using different answers. So we've got to look. If we look at wave A and wave B, without even looking at the question, what is different? Well, we can see actually, if we draw a line across, the bottom of the wave and the top of the wave is exactly the same height. Okay? That height there and that height there is exactly the same, and that's what we call amplitude. So we already know they have the same amplitude. So what is actually different? Well, get rid of those lines for a second. What is the gap between the waves? Well, they've got squares on them, which helps us, because then we can see that actually this difference between the waves, or distance between the waves, is different. Wave B, well, the distance is always the wavelength, but we can see that wave B has a longer wavelength. If you look at the figure, put what I put on the figure, do that sort of thing first before you look at the question. The question's easy. The question's just, do you understand how to put those words into the answer? So here we go. A difference. Wave A has a greater. Ooh, we didn't actually write this down. We didn't say wave. We wrote wavelength. Okay, but wave A doesn't have a greater wavelength, so we know it cannot be that one. Wave A doesn't have a greater amplitude, so we know it can't be that one. So now we have a choice between frequency or period, and we've got to understand that if wave A has a shorter wavelength, okay, so wave A has a short wavelength, that means it's going to have a greater or a higher frequency, because they go hand in hand. If one increases, the other one is going to decrease. So that's our difference. And then wave A has the same. Well, we've looked at that. We've said it has the same amplitude, so it has to be amplitude because we've already looked at it as part of our question, as part of looking through the figure beforehand. Now, which of the following is the same as 4.0 kilohertz? Now look at that K. That K, or kilohertz, if we put it out, means 1,000 hertz. Kilo literally means 1,000. So therefore, what is 4,000 hertz? Well, that's 4,000 hertz. And you have to know the K means 1,000. Calculate the period of A. Use your answer from question 3.4. Again, this is good. If it says use your answer 3.4, don't worry about whether you got 3.4 wrong. It will give you the marks, even if you got that wrong. So always use it. Always attempt it. Even if you think 3.4 is totally wrong, you made a crazy guess, you can still get the marks for 3.5. Okay? And again, look at the number of marks. 2 marks means you're going to write some stuff down. No rearranging, no solving for something different, and then you're going to put it into your calculator. So, what does it say? It says calculate the period. Well, we're going to write period equals 1 over And then we worked out the frequency as 4,000. And so our answer is going to be, if we put that into a calculator, lots of zeros, so 0.00025. Some people's calculators may not do it like that. They may actually do it as standard form, and that is acceptable. It may say 2.45 times 10 to the minus 4. That is also acceptable as an answer, so don't worry if your calculator says that. Okay, complete the sentence. Again, looking, choose the answers from the box. It doesn't say you use them twice, which means you're not going to. It's only 2 marks, so it's just fill in the blanks. When sound waves travel through the air, they create areas of. Now, this is knowing that as a sound wave travels, there are areas where lots of sound waves are put together, close together, and lots of sound, and then the waves are farther apart. Okay? They're different. So there is no correct order to this. It can either be compression first, doesn't matter if it's not first, or rarefaction. Both are acceptable in either order, but it is knowing those terms. That's what is important. Okay, now we have about magnets. It shows a permanent magnet and 2 magnetic compasses. Important for this is understanding. So we're going to look at the question first. Well, actually, we're not going to look at the question at all, sorry. We're going to look at the figure. The figure is really important because it's got 2 compasses and it's got a magnet in the middle, but it doesn't say north or south on it. But it does have a compass on it, and the compass has an arrow pointing towards X. Now, one really important thing you need to know about magnets is that the magnetic field always goes from north to south. So if the arrow is pointing into X, that means X must be south, which means Y must be north. Just doing that without even looking at the question is going to help you. That's the science about what we're looking at, okay? When we look at the question, it says, give the names of the poles labeled X and Y. Oh, well, that's really easy. We've already written that on our diagram. It's south and north. That's why looking at the figure rather than jumping straight to the question is important. It then says draw an arrow on compass B to show the direction of the magnetic field. Well, if you look at what I've drawn here, I'm highlighting it as really important. We've got arrows coming out of north, which means your arrow is going to be coming out of that circle for compass B. Okay, we have a figure of some genes with security tags. It's not a scientific diagram, so it's not as important to us. We don't have to spend loads of time on it. But it then has which of the following are magnetic materials. Well, we look at the marks. It's only worth 2 marks. It also says tick 2 boxes, which means we're going to get 1 mark for each. So then we have to look through. You have to know certain magnetic materials. You just have to know them. Iron is one of those magnetic materials, and nickel is the other one. Okay? You need to know that it's iron, or nickel, or cobalt, or steel. Steel is obviously not a metal, it's a material because it's an alloy. Okay, which of the following describes the force between a magnetic field and a magnet? Now this is really important. A magnetic material, and a magnet. Well, if I have my magnet here, and I put a material next to it, that is magnetic, what's going to happen to it? It's going to go towards the magnet. If I put a magnetic material here, it's going to go towards the magnet, which means it's always attracted. Always going to be attracted to the magnet. And 4.5, the shop assistant removes a security tag, drops the tag into a collecting bin, calculate the resultant force acting on the bag. Okay, they give you the equation, look at the number of marks, it's only worth 2, which means we're going to be doing the simpler version. We're calculating resultant force. Our mass is 0.030. That's from the question. And then we're going to times it by acceleration again, which is 9.8. In the question, you get 1 mark for writing it exactly like that, and you get your other mark for writing the answer. That's where the 2 marks come from. So never ever miss that first step. Okay, stopping distance. It's good to give you an idea at the beginning of every question. We're talking about stopping distance, braking, thinking distance. And so 5.1, which of the following affects the thinking distance? Thinking is brain related. Brain and body, mostly brain really. Okay, are the brakes going to be affected by your brain? No, they're not. Are the icy road conditions? No, they're not. Is the reaction time of the driver, well, we're talking about the driver here, so absolutely yes it is. And then we have a method. Lovely, great, fantastic. Well, let's look at the question first. The brakes were applied with the same force for each test. That's important, so the same force. Give one other variable that should have been kept the same for each test. So we know same force is a control variable. Okay, so that means we're looking for another. If we're keeping it the same, we're looking for another control variable. So let's look at our method. Car manufacturer tested 3 different types of tire. That's our independent variable, which were fitted to 3 identical cars. They drove the car along the road, applied the brakes until the car stopped, measure the distance. That's our dependent variable. It just helps us work out. We're not going to be keeping the distance the same because that's what we're measuring. We're not going to be keeping the type of tire the same because that's what we're changing. And then it says repeat the steps for each car when the road is dry and when the road is wet. Okay? Are those things that we need to keep the same? Well, they've already given us that one. And the question says one other variable. So it cannot be really that because they've already given us that one. Okay? What is going to affect the speed or the distance the driver stops at? You should know that you may have been shown it in class. The different distances based on, if we almost have that as a graph, these are the speed of the car and this is the distance of the car. The distance is massively increasing. In fact, that's absolutely not the right way around. Let's try that again. Okay. As the speed increases, so really we probably should put it the other way around, shouldn't we? So as the speed increases, the distance also increases. So if the speed increases, the distance is also going to increase. If the distance is increasing, that means speed is increasing. And if we have the same force, and we're going to change the road already, we need to keep the same initial speed. We only want to see the tires. We don't want anything else to affect the distance the car travels. We only want to see the tires have an effect. Not the road, they've already talked about. Not the brakes, because they've already talked about it in the question. They said the same force. So now it's actually just the speed we need to look at. Okay, we have a figure, and it's figure 10. It's a big figure, which is important, meaning we should look at it before we even look at our question. Okay? We should be looking at everything and comparing some things. That's what's really important. So we can write, I always like to write the numbers in. So for our dry road, that's 30, and that's 31, that's 42, that's 43. Sort of helps, so I don't have to keep on looking at it if I do it first. Okay, so we've got our numbers in at least. Now we can look at which do we think is the best tire on wet. So which is the one on wet and which is the one on dry? Because that's going to be important. Okay, we want the distance to be the shortest as possible. So on a dry road, the dry road is our dark grey one, and out of 3 of those, that is tire C. Okay? It would help if I wrote it the correct way around though, wouldn't it? So the best on the dry road is tire C. However, the best on the wet road is the light grey, and that's actually 31, which is tire A. Okay, so it's useful to be able to just straight away go, okay, tire C is the best on dry, tire A is the best on wet. We've got some numbers here. Which is the worst? The worst is by far and away tire B, because it's the worst of both. It's generally just the worst. Okay. Okay, it's really important for this question because we've already done the bar chart and we looked at it, we wrote lots of things down. This is just where we add to it. So when it says use the data, we're essentially going to be writing down what we've just said, what we've talked about. So we can start with how we judged anything. We can say the first thing is the shorter the distance, or the braking distance, the safer the tire, right? It's really important to sort of put that in there, as that's our basis, that's our judgment, or the basis for any of our judgments for this question. So therefore, when we start saying tire A is the best for this, tire B is the best for this, or worse for this, there's a basis for that. The shorter the distance is the safer the tire. So we can start with tire B is worst for wet and dry. Right, we can say that because it has the longest distance for both of them, which is absolutely fine. Okay. We then said two different things. We said tire A has the shortest distance Tire A has shortest braking distance on wet road. That's what it said already. Okay, and then we can say tire C has the shortest distance on dry road. Okay, straight away we've said that. We can put the numbers in there, so we can say for tire C on a dry road it's 29 meters. For tire A on a wet road we can say it is 31 meters, so we can add that. All of those things, not a problem at all. Okay, we can say the difference between them as well, but this is the point where it says evaluate. This is our evaluation. This is what gets us our marks because we have a judgment. So we can say tire C is safest on dry, tire A is safest on wet. Overall, we think tire A is safest because it's not bad on dry road either. So we can talk about actually on dry road it's only 30 meters. On dry road that's only 1 meter longer than tire C. Okay, that's our conclusion. This really important overall bit, that's our conclusion, which is what's going to take us to those higher 4, 5 and 6 marks for this question. Write down an equation. If you have an equation sheet, which you do in this exam, there's no way you can get this wrong. You should be able to get this wrong. You can use the words. If you're confident using the symbols, you've got to be able to use the capital letters correctly. W equals Fs. Easy as that. You can also put a times F times S if you want to as well. Now for this one, because it says 3 marks and calculate, that means we're going to be doing an extra step. That tells you straight away, those 3 marks tells you that, okay? So if we have our equation and it tells us the work done is this, we're going to do 300,000 equals our force, which is 6,000 times by S. That is going to get us 1 mark. We are then going to do the opposite function for 6,000, so we're going to do 300,000 divided by 6,000 equals S. That's going to get us the 2nd mark because we've shown we know how to solve for S. And then if we do that calculation, the braking distance is 50 meters. That's our 3rd mark for this question. Make sure you can put the numbers into the equations. Then explain how the force applied by the brakes affects the braking distance. Okay, it's an explain question, so somewhere in this question you need to have a so, or a because, or a therefore. Okay, well the first one, it's almost like a describe bit. The greater the force, the greater the force, the more force the brakes have, So the more force the brakes put onto the tyres, the shorter the distance, the braking distance. Okay? That's your description, that's not an explanation. So therefore you need to say, so that makes an explanation. The deceleration will be greater. Okay, now you might think, where do we get deceleration from? Right, that's not even in the previous bit of the question. If we don't want to do the deceleration, that's not a problem. You can do a so instead and link it to our equation which we just did, which was work done equals force times distance. Well, if we said the greater the force, the shorter the distance, that is because if force increases and F decreases, that means work done is going to be the same. So work done to stop the car is the same. And that's important actually, because it's only if one increases and one decreases by the same quantity, then W is going to be the same. The work done will always be the same number. Okay, then we have 6. We have a describe a method. This is our crossover question, one of our crossover questions for higher as well. And it's describe a method, which means we're going to be doing step 1, do this, step 2, do this, all those sorts of things, and how to make our method accurate as well. It's 4 marks, it's not a full 6 mark, so there's going to be less you have to include, but it's still important, okay? So what do we have here in our diagram? Again, we've got a figure, it's useful to use. Signal generator. What is the point of signal generator? That is for frequency. Okay, it's really important. Okay, what's the point of the masses? Well, we just have them there so that they're there, but we need to say we're going to keep the same mass every time we do this, okay? And I have a movable bridge. What are we going to move? Shockingly, it's the movable bridge. So this is going to be our independent variable. This is going to be our control variable, okay? And we're going to move the adjustable bridge, potentially, but actually we're going to adjust the frequency potentially too. What are we going to measure? Well, that's where, again, labeling the diagram is important. We're going to measure the length. That is our dependent variable as well. And what do we need to do to investigate how the frequency affects the wavelength? Well, we've said our independent variable could be the movable wooden bridge, but actually that's why reading the questions is important, because frequency is what we're actually going to change, is our independent variable, and wavelength is what we're going to keep the same. Is what we're going to measure, sorry. That's our dependent variable. So how do we put this all together? Well, we're going to have signal generator. This is why a diagram is so important, because it basically gives us the answer for us. Signal generator adjusts frequency or changes frequency. That's our independent variable. Okay, masses are the same, right? Just saying masses are the same, that's your control variable. Okay, we move the bridge. Now, why are we moving the wooden bridge? We want to move the wooden bridge to make sure that the string stays relatively taut. Okay, now once we've done this, we observe, we look for a standing wave. That's where it doesn't look like it's wobbling like on a slinky. It almost looks like it's magically staying still, even though it's not really. Okay, then we measure wavelength, but again, if you notice, there isn't a piece of equipment for measure. Oh, yes, there is. There's meter ruler. So we need to say use meter rule. That's important. Okay, that's our method. We've done it once. What do? This is where it comes into getting up to those 3 or 4 marks. Repeat. So we're going to repeat with different frequencies. That's our independent variable, because we're repeating it and we're changing the frequency. And what else? Well, repeat 3 times, remove anomalies, always, 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 last but not least, calculate a mean. Okay, it's always just include that every single time. It's good practice. Use our physics equation sheet. Again, you've got your physics equation sheet. You should be able to do this correctly, and it's wave speed is frequency times wavelength. We are then using it again. Look how many marks. It's 3 marks, which means we're going to be doing 2 things. So what have we got? Well, we have wave speed, that's 35.1, and it's going to equal the frequency, which is 45.0, times by the wavelength, but we don't have that. That gets you 1 mark just for substituting in the numbers. We then do 35.1, and again we've done the reverse function to do 35.1 divided by 45.0. That's our second mark, and then if we put it into our calculator, we get our third mark of 0.78. Okay, we get to our slightly bigger question. Although it doesn't seem so, we've got a figure, and there's quite a bit of science within this question. When a spring is compressed, the elastic potential energy of the spring increases. Explain why compressing the springs in the floor help the gymnast to jump higher. And crucially, it says use ideas about energy, which means you're going to be talking, as much as you might want to talk about force or anything else, we're talking about energy here, because they've asked us to talk about energy. And it's 2 marks, which means there need to be 2 things we're going to say. So we can say they've already talked about it compressing. So we don't need to talk about it compressing, because they've already said when the elastic potential energy of the spring increases. What we need to say is essentially the opposite. And you can talk about compressing. You need to know compressing is when it's squeezed. So it's essentially when they land on the spring, it's going to compress, and then it's going to be extended afterwards. So we can say when the spring, and we can say it in lots of different ways, but we'll say when the spring decompresses, because that's quite literally the opposite. The elastic potential energy, and again, I'm going to shorten it here, but elastic potential energy, they've used that phrase, so it's worthwhile you writing it down. Decompresses, the elastic potential energy of the spring decreases. Okay, that's just saying when the spring stops being squeezed, a lot of the elastic potential energy is going to decrease. Now, where's it going? Because if you imagine this is my spring, and there's lots of elastic potential energy there, where's it being transferred to? Well, you're going up in the air, so that's my gravitational potential energy, but also you're going to start moving, so it's going to be kinetic. So I would say for both my gravitational and my kinetic energy store are both increasing. That is what's happening. Very much that diagram of if it goes from one, if energy is stored in one place, it's going to be transferred to another place. And the elastic potential energy has been transferred to the gravitational potential energy store and the kinetic energy store. And the gymnast last on the floor. Okay, now for me, I'm looking at, it says calculate the elastic potential energy stored in the spring. Use the physics equation sheet, so they're going to give you an equation, but of course you're going to have that equation anyway. And it's also 4 marks, which means there's quite a few marks needed for this. It's not just a plug sort of numbers in, substitute numbers in. It means you'll get a mark for the unit, but you'll also, it's 3 marks, which means you're still going to have to do something else. It's either going to be a conversion or it's going to be a rearrangement. So if we look at the numbers, that's problematic straight away, because we don't measure things in centimeters, which means we have to straight away change that to 0.012 meters. Boom. We've got ourselves a mark straight away. Okay. Now, if we look at our physics equation sheet, we have elastic potential energy equals half times by spring constant times by extension squared. That's our equation. So if we substitute our numbers in, that's going to be half times by 8,500 times by 0.012 squared. Again, important, quite easy to forget that square, miss that out. and if we plug all that in, we are going to end up with a number of 0.612. And again, the unit, we're looking at energy here, aren't we? There's only one unit for energy. It doesn't matter what store of energy it is. It's always going to be in joules. Okay, describe how the compression of the spring could be determined. Now, this is an interesting one because they're talking about compression of a spring, not extension of a spring. In your required practical for this topic, it is all about the extension of a spring, and this is compression. It's very similar though. In fact, it's the same method, just the spring is going to get smaller or shorter in length rather than longer in length. So what we need to do is, if we remember how to do that, it is measure the length of the spring, but it's not just measure the length of the spring. You don't just measure it once. You measure the length of the string before and after compression. Okay, you need to do that before and after, or rather, maybe not after compression, or during compression actually. Before and during compression, because it's not after it. Okay, so you're going to measure the length of the spring and measure the length of the spring when it's being compressed. And then what you're going to do is the compression is going to equal, this is how we did it, we calculate the difference between, don't we? So we do original, that's the before, and we take away the compressed length. And that's going to tell us by how much the spring was compressed. That's our description. That's just asking you one of the techniques, one of the most important techniques really for that practical, is how do we measure the extension or compression of a spring. Next one is explain why the investigation should be done on a laboratory floor rather than on a table. Well, these are, again, what are the risks, hazards associated with this? Well, masses could fall. Okay, if a mass falls off, that could cause injury or damage the floor. Could injure someone or damage the floor. Okay, you might think, what on earth, how is that science? Well, part of science, especially when we're doing investigations, is designing a practical that's not going to hurt people or damage the building around us, or our apparatus at least. Okay, now it says determine the value delta y. Well, they've drawn the line of best fit, trend line, they've put the lines on it for us to be able to calculate the gradient probably eventually. So all we need to do is we need to go all the way across here in the most beautiful straight lines ever to work out that that is 330, and then we go all the way along the bottom and work out that that is 80, and that little triangle means change or difference. So 330 take away 80 is 250 newtons. And if you notice, the next question is pretty much the same. Opposite, this time it is determine what it is for x. Again, if you actually have a ruler, you can do it much, much better than I can. 0.052. Same thing, take away 0.010. Lots of zeros in there. We end up with that calculation, or not that answer really, for the value of change in x. This is really important because it's 2 marks, which means you're plugging numbers, you're just substituting numbers in. It's nothing that complicated. And again, use your answers. So even if you guessed the previous 2, or you like, oh, I'm not sure if I got the scale correct, you can use those answers. It's not a problem, okay? And then give your answer 3 significant figures. That's probably the most important bit, to be honest, to get that 3rd mark, or 2nd mark, I should say. So we substitute in our values. K equals 250 divided by 0.042. Those are the 2 numbers we've already come out with. And our answer is, for this, our answer is 5952.38. Okay, but they've asked us for 2 significant figures, so we need to draw a line and decide whether we're going to round it up. In fact, that is totally the wrong place because it's 3 significant figures, not 4. We're going to draw a line there, and because the 2 is smaller than 5, we're not going to round it up. So we're going to end up with 5,950 Newton meters, and that's our second mark.